Okay, welcome to part two of devices. Previous section we discussed device states. We started to walk through the device template, and then we talked about device errors and triggering, things like that. We'll probably retouch that as well in this video, but now we're going to transition and talk about the device state engine. So jumping back in, the device state engine, we go back to our device template, come down, rung 3, we have our executor engine and debug. So this device state engine, again, it should be a part of every device state machine code that you run, but effectively this is the workhorse for our logic. Trying to utilize and make this logic work requires this device state engine. I will say it doesn't require it, but it definitely reduces a lot of the um, I guess code redevelopment. So it's got a lot of built-in goodies. So let's go ahead and pop into the device state engine. So obviously this was one of the first things I wrote. One of the first pieces of logic I developed. Okay, so purpose of this function block is to manage step changes and also offers a debugging mode to manage the step number transitions. So when we're transitioning between states, when PLC, the way the PLCs run, I mean, you can't, it goes so fast you can't detect it. So having that ability to step through your logic is certainly helpful, and this is built into this device state engine. Um, this also manages the reaction to our instant kill inputs, as well as some of the other instant inputs that we have. So again, like anytime the kill command comes in, that's happening through that instant kill input, and we're reacting to that in this device state engine logic. And then additionally, we also are monitoring how long we're sitting in our states. So typically, if you're sitting in a state for too long, that you shouldn't be sitting in for very long, then something likely went wrong. And so it's convenient for us to, rather than, stall out and stall out in a step number and it doesn't seem like anything's wrong to the outside world, we can issue a timeout error. And typically, when we're issuing timeout errors, it's likely something needs to be debugged on the engineer's side, or there's something just really, really off on the machine. So we should be trying to detect errors without having to lean on these step timeouts. But certainly, the step timeout does create the ability for us to have kind of a more robust solution to say, hey, we can, when we're not expecting to sit in a step for 5 minutes and we've been sitting there, we can trigger an error and we can get some intervention sooner rather than later. So I think that is the primary motivation for having these step timeouts. It was actually I this wasn't my idea. I have to give credit to a previous project. I was working a contract for a company out of Arizona, and the architecture that the gentleman was using involved this step timeout, and I thought it was pretty slick, so I took it. So thank you, Steve McDermott. um, But yeah, like I said, it's really just there to kind of like, if you haven't figured out there's an error already, it's just a catch-all. All right, kind of lost my train of thought. So what else? What else? What else? What else? Let's just walk through the logic. So we see here at the top, we got this reaction to an instant stop input. So when we have this instant stop input, basically we are enforcing that we're already in this idle, paused or running state. But basically when we see that instant stop input come on, um, we immediately assign the next step number to be stopping. So basically we're going to jump to on the next step, we're going to jump to stopping. The instant reset, when that comes on, we jump to this resetting step. It's convenient for me to use this enum that is corresponds to states to also use it as to write the step number. That way, when you're writing to these different step numbers in your state machine, the consistency that, the first step in resetting is step 50. It just keeps it consistent. The step number for idle is 100. The step number for inactive is 0. It just allows the engineer to um, have to go back and maybe edit the step number if it should change, but it's just really there as a convenience factor. So you don't have to remember the step number. It's already built into this enum. So yeah, instant manual, kind of same thing, just writes the step number. Instant kill, we jump to this aborting step. Um, so the step change manager, this is actually what is responsible for allowing us to transition. So when in a normal case, when we're not in the step mode, we are saying, okay, um, you know, when we were in a step where we were trying to transition, let's say we're in the faulted step, someone cleared our errors, and we set the next step number to an active, to step 0. Basically, in this step change manager, we're detecting that. We're saying, hey, the next step number, it's not where we are right now. So let's move the next step number. Let's make that our current step number. And this is the step number that gets relayed out to the world, to our parent. And then let's also, as a convenience, we'll set this first scan bit. And this first scan bit is first scan of that step. So anytime we first freshly enter a new step number, we set this first scan bit on for one cycle scan, and that allows us to do some initialization within our rung that is, associated with that step number. It's pretty convenient, and we'll kind of maybe we'll see that as I describe some of the other devices, but certainly is pretty convenient. Yeah, so that's what allows us to kind of change step numbers. If we are in a step mode, so if this step is true, then we will not transition to the next step number unless someone writes. Uh, you can manually set this go to next step bit to be true. Once that's true, it sets that on, and then of course we want to always reset our next step bit. So we generally reset that directly after that, so it's not stagnantly on. Yeah. So the state monitor, this is just, like I said, there's some redundancy in sort of the step number, the states, this idle state. So basically, I'm just saying, hey, if I'm in this if step number is 100, then um, I set my color code, I set my device state number, and I set this Boolean idle bit. And I do that for all the other states. So this one is for running. If I'm greater than idle, less than stopping, um, I'm running. If I'm paused, I'm paused. If I'm stopping, aborting. You get the picture. So faulted. Resetting, if I'm greater than equal to that first resetting step and less than idle, then resetting. Manual, if I'm in that manual step number 200 or 2000, then I'm in manual. And then this is where I combine those different states. So idle or faulted, killed, inactive, idle, faulted, manual. All that's there. Timeout error, this is where I'm just watching to see if the timeout, how long the step has been there. And I'm automatically issuing an error code um, based on the step number. I also add 10,000. So this is kind of a way for me on the user interface side. I can say, okay, if there's any error codes that are 10,000 or greater, then there must be um, there must be a step number fault. Yeah, and I'm not issuing these faults if we're done, if we're in this, for idle, inactive, faulted, killed, or manual. I'm not issuing, those steps you can sit in indefinitely for a long time. So I don't want to trigger a timeout fault in steps that I'm expecting to be sitting in, for a long, long, long time. And um, the other way I ignore the runout timer is if in a particular rung, if I set this engineering step timeout to be 0, then I won't basically run this run timeout timer. So this is the logic to run this timeout watchdog timer. So if this is never true, it won't ever trigger a fault. So programmatically, in each one of the rungs, I can create a custom timeout. By default, the step timeout is we're going to assign it this global constant, the step timeout, which is 5 seconds. But I can overwrite. You can see I should be writing this in my device rung, like the specific step number I'm in. Let's say I'm in step 500. I'm running. I set the engine dot step timeout to either 0 seconds or let's just say I set it to 0 seconds. I want to ignore it in this step. So basically, this is going to look at that logic. It's going to say, oh, the step number was, it was less than or equal, it was equal to 0, so this isn't true. But then right here, it sets it back. So I need to make sure in my actual rung that's executing, that I'm always writing that logic to engineering step timeout. So I shouldn't have any other logic in there other than, move. Hopefully I remember to delete this. Time 0 seconds to engineering step timeout. So I don't want to have any other logic in here. I always want to be setting it to 0. if I truly want to ignore that step timeout, or set it to something really large. Okay. Cycle time monitor. This is just some other built-in goodie. I can see I start the stopwatch when I transition from idle to running, and I stop it when I'm transitioned to done. And so you could look and see, how long it took you to do a cycle by just looking at uh, this rung here. Not a lot of logic that we use. Actually, this doesn't really come in handy, but it may for future purposes, but just a good thing to have in there. So that's the device state engine. So going back to the device template, we have the basically all the necessary states and step numbers associated with them. So we have this faulted step. We're only transitioning out of that when we don't have any errors. Our children don't have any errors. We're in this killed state. We don't leave it until the kill command is dropped. Inactive, basically we're waiting to be reset. Resetting, I give you a step 50 here, and then you could transition to, you may have multiple steps. So I kind of just generically said, oh, reset your children, reset yourself, and then jump to idle. So in idle, waiting for a start command. Once your start command, jump to this running step. Once you're running, then blah blah blah. Insert some logic in here, then transition to done. When you're done, you've got the stopping reaction step. So you generally here are issuing stop commands to your children, and then you're looking to verify that they're idle or dead or errored or faulted, and then you transition then to aborting or to idle, depending on if there's errors present or not. Then you got aborting. Here you're generally just issuing kill commands to your children. Pausing, we're pushing pause on the robot or something, and then we go and enter the pause state. Wait and pause until someone starts us up again, and then we go back to running step. So it's just kind of in there. It's not really used much in the logic. Then we have this done step, step 1000. Sit here until the start command or task command, whatever is dropped. And then go back to idle. And then you got this manual control step. But yeah, fault reset. This is actually kind of deprecated. It's not really used anymore. The actual fault clearing occurs in this fault monitor at the system level. Down here, insert some logic for some reaction-based stuff, like if you're monitoring some conditions or cases. This is just a placeholder to add a bunch of different rungs in here for monitors and managers. And then child devices. This is where you need to add in your function block to call your children. So we saw that, I think, in the previous video. We looked at child devices. We had, for the conductor, that's got the rack, it's got the robot, it's got the CNC. When I added those children devices within my variable declaration, I had to modify this data type called child array. So I added in the device IDs of my children. So you can see in the device template function block, when you cut and copy paste this code, it's all zeros. But if you truly had children, you'd add the function block here, and then you would come in here and you would say, device IDs dot, whatever your child was. And then you write it in there. And then, you got a value. But yeah, you want to make sure that this array has 10 values, or however many values this global constant here has. yeah, I think that about does it for this video. That was, I guess maybe we'll call that part two, so the device state engine. And I think the next part, we'll actually go through a demo and I'll show you how to add a device into the logic. There's several places that we kind of have to do some housekeeping. So I'll show you how to do that with the washer. So we'll just kind of go through and I'll show you how we insert that. So thank you very much.